welcome. We're going to talk about deploying like a boss, from the journey really from 2 servers up to tens of thousands. So my name's Oliver Nicholas, sometimes known by the handle Big O, for obvious reasons at 5'9". We're going to talk about deployments, which is really a thrilling topic most of the time. In this context, we're basically talking about the act of taking your code from one place and then putting it in another place. You'll have to excuse my absurd use of transition effects. This isn't my first rodeo, but these are like too much fun not to use. So it's a little more exciting than just moving bits around. We also need to touch on load balancer management, which is another really terrible dinner table conversation topic, and also the distribution of these build artifacts. I know this was the last talk before lunch. I remember reading a study that was like, if this was a parole board hearing, I would have a really low chance of getting parole. So just stick with me. I promise it'll be sort of interesting. First off, quick background, who I am and what right I have to talk about this for a little while. I work as a staff engineer these days with Uber Technologies Incorporated. We are what's known as a TNC, Transportation Network Company, in that we make this remarkably popular app which connects independent operators with folks who are trying to get places. We do this in 311 cities across 57 countries, over 1 million times per day. More relevant to this talk, on the back end, we do that with about 300 separate micro to macro services. These are sort of different orders of magnitude of traffic that these services serve. Deployed across somewhere around 2,000 to 3,000 servers per data center. And we're sort of constantly changing this, but it's between 2 and 4 data centers right now, always be scaling. And excuse me, we do at least tens of deployments per day across all of our services. So it's a very active environment, and code is moving around really frequently. And we want to keep agile. We want to be able to make deployments all the time, not worry too much about them. Crucially, you want to be able to roll them back as well. Me personally, made my first web page in 7th grade. I was really proud of that, sometime around 96. So I've been working on this problem of how do you get your code from one place to another for a pretty long time. I took my first job at a tiny incubator in San Francisco called Ooga Labs. We were like 5 guys in a room big enough to hold 4 guys, I think. And our deployments there pretty frequently brought down the site. I took my second job in 2008 at Yelp. In my second week there, actually, I took down the site by deploying some code that worked with the version of Python that we had in the dev and stage environments, but didn't work with the version of Python that we were running in the production environment, which was a real good lesson learned about how you test code before it goes out. And then in 2012, I joined Uber, which, as I mentioned, we have a lot of code to move from place to place. When I got there, a little ways into the time I got there, we had scaled to a certain point. And at that point, I rewrote kind of the main deploy script, and then I gave it to other people so that they could use it to bring down the site from time to time. So that's sort of, I like to think of this as like a lessons learned through drastic mistakes and millions of dollars in lost revenue. It's a good way to internalize it all. So that's a bit about me. So what do we mean by a deployment system? This is a vague, broad term, I guess. By some measures, you could include build servers, CI servers, any other integration, pre-flight tests that you might have, the entire production serving infrastructure, the load balancers. But I want to talk specifically about the evolution of the piece that does the copying of the bits and sort of brings them live. So that is distribution and orchestration. So let's dive in and look first at sort of a typical nascent deployment system when you first get started on a project. I find that, that's brutal, but I find that frequently this is basically the first incarnation of a deploy script for most projects that are out there. You just press like up in your terminal or search your bash history for the last time you executed this command from your local like development box, and you use this old school tar SCP combination. In case there's anybody who's like not familiar with this, tar is this. Tar dates to 1979 and is literally, it's like tape archive. It does lots of things. In our use case, it takes a directory and combines it down into a single file, which you can then copy over to another server and then untar it and sort of reinflate the original directory structure. SCP, really hope everyone knows that one. The secure copy just sends your bits over a SSH connection. If you want to get like real janky, you could use RCP and not bother with all that pesky encryption. And then the second command that we see in this pipeline, which does a tar, pipes the output of that to an SSH command, which then executes some code remotely. The second part just untars it on the destination host. And then the third piece at the end there just like restarts your code. It starts the new code up. And actually, this is, you can build on this. There's actually programs that do combine a few of these steps down. There's Rsync. That's a pretty typical one. You'll just, you're writing your code, you hit that, go back to your bash history, hit your rsync command, and it just syncs the changed files. This is basically what rsync is good at. It examines the mod times on your files and maybe hashes of them, and then decides what actually needs to get transferred over the wire. And then the last part there, right, is just restarting the process. The drawbacks of this, it's not atomic. You're changing the code files while the code is running, which means if you get some module that hadn't been loaded yet that is suddenly loaded by a new request that comes in, you'll get mixed versions of your files running like in program space. There can be a performance impact during this process because you're doing a bunch of work on the host that's actually running the code before you even do the deployment. There's no load balancer management. I mean, this restart right here, depending on how you've written it, that might just like kill the process and start it up again. So you might drop existing connections. You might have your app be inaccessible for a while this is happening. It's just sort of a brittle process. The great thing about this is that it's real damn easy to do, and at this stage, you probably don't care about dropping traffic. You may not have that many requests coming in, or it might not cost you any money if you drop some hits. So this is really how I think most projects start out, and it's a totally appropriate way, I think, to start most projects, especially when you only have a single server that you're deploying to. But if you're lucky, the project grows up. And so we'll move here to the Middle Ages, I call them, where we have some existing projects out there that help us do deployments that are really, like, relatively speaking, quite robust and can take you pretty far. And in fact, can take you a little too far in that you end up with some pretty painful situations as you start to scale up. The middle stage deployment systems, you end up with these third-party libraries like Capistrano and Fabric. This is really identifiable as an evolution of this tar SCP pipeline. These libraries are just these DSLs written in higher level languages. Cap is Ruby, Fabric is a Python library. And they basically are just encapsulating your SSH session management. They come with all these convenience methods for things like unattended sudo passwords, copying files around, capturing and parsing standard out, even rollbacks. You go pretty far on these. Typical setup could involve all the stuff we see here, like build the code, sync it to deploy targets, take the target out of the load balancer, shut down the app, swap out a symlink to put the new version of the app in place, start the app up, heart checks, health checks, warm up, put the target back into the load balancer, and then move on to the next host. And these things are so, like Capistrano, Fabric, there's so much convenience to them that with about this much code, this is, I don't know, 10, 15 lines, you can actually get all of those steps that are right there. So this is pretty powerful stuff that really takes you pretty far. The pros here is that these are open source libraries. They've already been written for you. They're really easy to use. There's lots of recipes out there for the special, like any sort of special case you may have, pretty much any weird deployment workflow you want to do. Somebody has probably already written the code for you. And realistically, they are good enough for really into the tens of servers. After that, you start to run into weird issues. Things are always going wrong with at least one server when you have more than tens of them, or even like 50 of them maybe. Then your script one day does something really stupid. It tries to open 100 SSH connections at once, overloads something or other. Things really start to fall over. And so you have to do a lot more tuning, a lot of careful work after tens of servers, I find. And then the cons, this is really not good enough for hundreds of servers. You're still essentially utilizing this old school tar SCP pipeline, which is to say that you have a single node that has your canonical copy of your code on it, and it becomes pretty easy to knock that or something else over, like an entire rack. When you have 100, 200, 300 production servers, and all at once you ask all of them to download a 300 meg tar file from this one central server. You can extend away from that. I think when I arrived at Uber, the deploy scripts, generally speaking, would SSH to each machine and do a git pull. They're actually keeping a local copy of a git clone of the repo, and then do a build on that host. But that's got all sorts of problems with where you're doing the build work. It's very expensive. It's not particularly secure. A bunch of issues there. And then these have poor support for multi-user environments. There's no lock around the deployment process. Although you can resolve this, we have a deploy 01, and that's your deployment server, and you have to SSH in there, and it uses some F-locking to prevent multiple people from running it. But really, this doesn't feel good once you're sort of tens of employees. It's harder to coordinate your deploys, and you have a lot of servers to go to. It really starts to get quite brittle. Quick aside here. Build distribution. This is the actual copying of the bits. Until now, we've been running SCP, Rsync, whatever, from a single host, or maybe doing this really weird thing with doing git pulls on your remote host. But you're still then pulling the git repo from a single git server. This is really not going to last very long before you start to run into some difficult situations. We really want to avoid this single point of failure. Because those single points of failure, especially when you're running your own full racks, you can really knock over other pieces of infrastructure as well, which is not pretty to do. So more scalable approaches. We can do tiered Rsync hosts. So we can, instead of just having the code go to one server, we can rsync it to 3 or 4 intermediate hosts, some like logarithmic number of the total number of deploy hosts, and then your deploy targets randomly pick one of those hosts to rsync from. Probably more popular as you get a little bigger, you can stick these in some sort of equivalent or some sort of distributed file system. HDFS would be the popular one. I wouldn't advise playing too much with NFS for this, but perfectly doable. And then you get more into the more exotic options. I know Facebook uses BitTorrent to distribute their build artifact. Now, their build artifact, as I understand it, is a single multi-gigabyte executable. So, BitTorrent is good for this because it's good at chunking up large files and efficiently distributing that around. You can do all sorts of really neat stuff like make sure prefer peers that are on the same rack as you, so you get a lot of benefits from network locality. But this is a little more, you have to write your own BitTorrent clients and servers for this. But really these sort of tiered hosts or distributed file systems are a definite need once you get to hundreds of servers. And then they're an absolute requirement once you get to thousands. OK, so the early ages out of the way, we've looked at the intermediate systems. Let's see what we can do after tens of servers for the actual orchestration. How can we reimagine this whole model in a more scalable way? The real underlying issue here is that all of these systems were push-based. In general, anytime that you are doing work from one server out to other servers where the number of outbound connections is a factor of your scaling of your service, you're gonna run into problems. This is just sort of a general scaling principle, I think. When you have servers become inaccessible during the deployment with these old school systems, you get all these weird structural issues, especially if you're hitting them serially, one after the other, if the host isn't down, if it's not responding, if it's overloaded, if the rack it's on is overloaded, all sorts of stuff can happen. And then when that happens, you have to make pretty difficult decisions about what to do. A server doesn't respond. Do you abort the whole deploy? Do you roll back the whole deploy? Do you keep rolling forward? How long do you wait for? Does this mean that all of your deployments take 6 hours because you sort of hit the button and walk away and then don't realize that there's 5 hosts that are inaccessible? And then if you do keep rolling, you end up with this, in the push model, you end up with this painful consistency problem where when your old servers come back online, they miss the message that they were supposed to upgrade, and then they're running old versions of the code, and nobody really knows about it, and so you've got mixed versions in production. So we can resolve this by inverting the logic to be a sort of pull-based model where our leaf nodes, the app servers, are going to ping into a central server and say, what should I be doing here, rather than relying on this push. This is a pretty typical, I think, inversion of control, typical, I think, scaling property. This is sort of a goal-based system where these leaf servers are going to say, what state should I be in? And then they're going to do the work on their own. They're going to orchestrate it on their own to get into that state. Also, once you get past a couple of apps and a couple of servers that you're deploying to, it starts to get pretty inconvenient in those old school scripts where you have this, hard to go back, but where you have this list of servers. You know, this app deploys on servers 1, 6, 5. That it starts to feel really ugly to work with. And the data is hard to get to. It's not easy to share between scripts that might need that information about which service is deployed where. So specifically at Uber, we solved this with essentially this hardware management database called CUSTO. This was a project that was written by the guys at Dig back in the day. And it's really just this management database that consists of server objects and pools. And then you can either look up information by pool or by server. So you can tell from this data here that app01 is in the production rack 001, service A, and service B pools. And then you could also look up and say, which are the servers that are in the service A pool. And so you get this programmatic interface to finding out where your hardware is. CUSTO itself also, these server objects are pretty rich. And so we actually store all the information about how much memory is on this machine, how much disk space, what CPUs, that kind of stuff. I highly recommend this once you get to a certain size of infrastructure if you're running your own servers, a little less relevant if you're on AWS or something similar. OK, so we have this pull model, and how do we put that into play? We built our own thing called udeploy, which is The specification for it is only slightly less fuzzy than it's showing up on here. Basically, there's a coordinator in each data center, which is the box inside the box on top there. And then these big black boxes are data centers. The coordinator on the bottom is called an intermediate. And then a worker on every deploy target. Every app host that we're running, we put one of these workers on. The workers are polling the coordinator every so often for their target state. What should I be doing? What versions of the code should I have locally? What should I be running? That kind of a thing. The coordinator hits this CUSTO database and has this a priori concept of which machines are in the service pool, and then it can use that and a associated deploy policy for every individual service that it knows about to decide how to instruct these servers when they do make requests, how to proceed. This deployment policy is customizable. So you can say things like, the coordinator can proceed with actually kicking off the deploy once 90% of the servers have downloaded the code. And so this allows you to sort of automate the consistency issues that you might have with a really large infrastructure and machines that periodically come in and go out of availability. And then the intermediate coordinators take a cue from the primary as soon as deployments are kind of started. So we actually perform our deployments in parallel across data centers. This becomes pretty important, since every new data center is essentially, another 2,000 machines that we have to think about. So this is the goal-based system. Incidentally, the way we have it configured, these coordinators are pinging, these workers are pinging the coordinator every 30 seconds or so. And then as soon as you start kicking off a deploy in the udeploy UI, which I'll show you in a second, the next time one of those workers pings the coordinator for a state update, and the coordinator knows that that worker is from a machine that's going to be involved in this deploy, it says, go into overdrive, ping me every 5 seconds. And that way we can sort of reduce, in the general case, we don't have too much load on the coordinator, but when we're actually doing a deployment, the machines that are relevant to it, they'll ping more often, and we can more tightly coordinate the timeline to do a faster deploy. So I'll show a couple pieces here. This is sort of the first page you'd see. These are all the things that have API in the name. And it's kind of nice. You get the app itself, the type of app. There's a Node app in there, some Python apps, some basic static pages. You see how many instances are there and health of them. So we can see on this third one down that 4 of these instances are in some bad state, and the rest are in a good state, which is pretty cool. We see what we've actually deployed, when we did it, status of the current deployment, I guess. This is sort of the control dashboard for pretty much all deployments at Uber. This would be where you drill down into a single service. It's basically impossible to see, but you're seeing that you can actually deploy between stage or production environments. You can target these separately. And then on the bottom here, you're actually seeing state of every server that's running this code. So when those leaf nodes when those workers are pinging in, they're giving status updates to the coordinator, and the coordinator can show them in this UI. So it's actually a pretty rich system that works well for sort of in the hundreds of servers, I think. I think there would be a bunch of issues once we got into tens of thousands for any given service, but works good up to this point. So you go into the coordinator and you would kick off a deploy. And what you're seeing here is for one of those API services, you hit the build button. And it's pretty cool. It goes and hits the Git repo and shows a list of the last commits. And you can pick one of them. And that's the one you're going to do a build of. Hit the button. So let's say in this case, it's version ABC. And it's going to go do a build and create the build artifact. In this case, it would be a Python virtual env, but it could be a Docker container in some cases, or it could be anything, any sort of artifact. Then next time the workers that are involved once the build is done, next time the workers that are on this service's machines, as CUSTO reports, next time they call in, the Coordinator is going to tell it, hey, the list of the versions of code that you should have includes this version ABC. And then once the coordinator, by its deployment policy, is satisfied that enough of the servers have the code, it can move on to the next phase of the deployment, where it starts activating them in tranches. They're just, as they ping in, it's going to say, the coordinator is going to know, oh, I've already done the first 2 windows, so now I'm doing servers 20 through 30. So when those guys come in, give them an updated indication of which version of the code that they should be running. And then the deploy targets actually manage their upgrades from there. Remove themselves from the load balancer, activate the new code, warm it up, and then return themselves into the production pool. So it really pushes work off of the coordinator, so that it's only really doing passive work in the order of the number of workers that are out there. Also, while this is happening, the coordinator is talking to other systems which are monitoring the health of the service that's being deployed. So we can look at things like response times that change, exception rates going up, and then the coordinator can then, from its angle, initiate a rollback. So it can, as those workers are pinging in every 5 seconds, it can say, oh, we have to either abort, or we can go back to the last version of the code, and we keep multiple versions of the code present on the deploy targets so that it's very quick to do the rollback. So there are some drawbacks. We still have these static server pools. They're in CUSTO rather than in a file, but it means that the deployment kind of relies on having this weird static mapping of service to server. It's slow to update, kind of awkward to deal with. And then it also means that the deploys have to be windowed rather than like a full red-black deployment. So if I have 10 servers in the API service pool, when I go to do a deployment, well, I can take like 2 of them out, upgrade them, put them back in. Take 2 more out, upgrade them, put them back in. The most that I can take out at any one time is essentially, it's a factor of how over-provisioned my service is, and how comfortable I am reducing capacity. So if you tune this wrong, a deployment that goes fine during low traffic could actually knock out your service during a high traffic period. And so because we only have those 10 servers to work with, so it can be a little constrained. So this is sort of the fun stuff. This is actually my current area of focus. This is what I'm myself working on right now. The future. Where are we going to take this so that we can overcome the remaining limitations until we find some more limitations? Quick poll, how many people here are familiar with Mesos? Oh, a good number. OK, cool. Well, Mesos is this resource management engine, pluggable conduit for scheduling tasks, jobs against server resources. The Mesos people call it a distributed systems kernel. There's a lot of great nomenclature around the Mesos ecosystem. This is kind of what it looks like. It's essentially cluster management. It's in the Apache Foundation right now. It consists of this. I'm afraid if this is a power button or a laser button, I'm not going to risk it. It consists of a high availability set of master nodes, which are coordinated by a zookeeper quorum, and then a slave instance that's running on every worker node. So that's actually in some ways kind of similar to how udeploy works. This is where it gets weird. These slaves, they make resource offers to the master. They say, I have so many CPUs, so much memory, so much disk space available. It's kind of cool. You can define custom resources that get offered through as well. And then the master is going to pass those offers onto these frameworks that it's configured with. In this case, I've put Marathon up there, but there's a jillion others. And then that framework gets to decide, do I have a job that I want to run that fits into this resource offer that I've just been given? I have this server. It's tagged as having kernel version 3.13, and I've been told that I have 12 cores and 24 gigs of RAM to work with. Do I want to schedule something here? And if it does want to accept it, then it passes back, this is how many resources my job needs. This is the job I want you to run. This is the job I want you to run. So then there's these sort of acknowledgements that go back and forth. Some sort of magic happens, and then your code starts running. And then the slave decrements its available resources. So the next time that it makes an offer, it's going to reflect the fact that you've just used up some of those cores and some of that RAM. And this doesn't really deal with the code distribution part. So all that stuff that we went over is still sort of relevant to this. This is a quick example. So a slave might make an offer, 22 cores and 32 gigs of RAM. The master sends it off to the frameworks. The framework might accept a portion of it and inform the master. So I want 1 CPU and I want 64 megs of RAM, and just run the command yes. You're probably familiar with it. Yes is like my favorite command to do this because it just chews up 1 core. The man page for it is probably my favorite man page in Unix. It's be repetitively affirmative is the only thing it says. Yes just prints yes, just standard out in a tight loop. Then the next offer would have taken that into account. This is all quite magic. It's fault tolerant. If the slave crashes, it's doing some checkpointing locally, and then when it starts back up, it can usually figure out where it was. You can also configure it so that if it crashes and it starts back up, that it can just declare bankruptcy, kill everything that's running, start over. If the master crashes, then there are these other masters in this quorum that can take over from it. And then the frameworks, it's kind of interesting. So the framework is the thing that cares about what's actually running. Mesos is tracking individual instances, but the framework is the one that scheduled the job in the first place. So the framework's the one ostensibly that cares about it. The framework is expected to make a durable commit about what it thinks the state of the cluster is just before it tells Mesos, this is what I want you to run. So if the framework crashes, when it starts back up, it has this list of tasks that it thinks it's scheduled, and then it can ask for this reconciliation process where it can say, hey, Mesos, what do you know about task A? And Mesos can check its state that's been communicated between slaves and master and say, this is the state. It's still running, it's good to go, or it's lost. It disappeared while you were gone, and you should update your own internal state to reflect that. And so that is Mesos pretty much. It's actually this remarkably simple system for apportioning out physical cluster resources to these frameworks that want to do work. And you can really run anything you want. You can run containers, you can run processes, you can sort of configure it any way you really want to. They've added in a bunch of really cool support for automatically setting C groups so you can get resource isolation. It's pretty great. Still sort of in the early days though, lots of work going on here. So we at Uber are specifically looking deep into starting to deploy a particular framework called Marathon. So this is one of those Mesos plugins, essentially. They describe it as a cluster-wide init and control system for services in C groups or Docker containers. It has built-in support for various deployment policies, similar to udeploy. It does its own health checking. It does automated rollbacks that are all configurable, which is pretty sweet. And I'll talk more about the overlap between this and udeploy in just a second. But it also has this really sweet constraint system. So I can say something like, given an app, I want you to distribute this evenly across racks, which is great for reducing the sort of failure modes of your application. You can tell it, don't put more than one instance of this app on any given server if you need that for some reason. Or you could say, only deploy to machines that have this certain tag on them, like a kernel version or a Python version or anything like that. So it's a pretty richly defined way to get specific constraints on your deployments. So this example I have right here is a really quick way to burn electricity. You can, with just a few clicks of this button, a few taps and a click of a button, you can deploy 300 instances of yes running across your infrastructure. And this is basically how I test things all day long. It's pretty fun. It also has this great REST API. So this UI you're seeing is really just a toy, really. OK, so how do we integrate these two things? What do we want to do by integrating them? udeploy has some awesome features in it already. It's got this beautiful interface for browsing our code repos and for kicking off builds. It has authentication and authorization support. If you're under PCI requirements, or if you have an organization of 600 engineers like we do, this stuff starts to become more important, and also probably very custom to your own organization. udeploy gives us coordination across multiple data centers. That is not a feature that's really in Mesos. Mesos is not designed to run across data centers. Zookeeper is definitely not designed to run across data centers, so this becomes sort of important. And we get this higher order health checking rollback functionality. We've customized it to look at our particular infrastructure and know what we think is a bad deploy. Look in our exception tracking systems, that kind of stuff. But Mesos and Marathon have some sweet features as well. They already built all this stuff for high availability masters with Zookeeper coordination. It's kind of nice to have that done already. Mesos really shifts the focus from individual instances to clusters of work. The Mesos slaves are tracking individual instances, but when an instance dies, it's not like, oh, this is the machine that was dedicated to run that instance. We have to restart it in place. It's, hey, something died, and the slave reports that back up to the master reports that to the framework decrements its run count by 1 and knows next time I get an offer, I need to schedule a new instance of this job somewhere on the infrastructure. So we don't really care about those individual instances because in a big enough infrastructure, things die all the time. You run into fatal exceptions left and right. You'll get a cosmic ray bit flip and suddenly something crashes. It just happens. So your ops team will definitely appreciate this characteristic. And it also homogenizes the cluster resources. So you're not really thinking as much about individual servers so much as a vast sea of CPUs and RAMs and disks and stuff. And that's probably what I just said. So what do we do? How are we going to combine these two? We're just going to mash them together. Good old composition. What we're actually going to do is we let udeploy kind of be the brain and the UI that decides what gets deployed and when it gets deployed, and it keeps watch over cluster health. And then we let Mesos, Marathon handle deployment strategies, resource allocation, instance health, that kind of stuff. First order approximation in this diagram. OK, so another neat thing is this makes auto-scaling much easier. By shifting the focus from where do you explicitly want instances to run to just give me some operating restrictions and tell me how many instances to run, Mesos Marathon really helps solve this doing the work part of scaling. It's easy to scale up the app. So what we want to automate is making the decision of scaling. So we're sort of starting to, this is still work in progress, I guess. We're starting to deal with this. Basically, we're looking at running everything that we deploy under a C group or under a Docker container. The infrastructure really supports both cases, but it gives you hard resource isolation among your running processes. This gives you fine-grained utilization metrics for every service that you're running across your infrastructure. And then from that, you can derive scaling decisions. So you can look at sort of global resource utilization for the API service and say, oh, this thing is getting to 90% of its CPU utilization. That probably indicates that it's serving too many requests for the amount of workers that are out there. Let's scale up the number of workers. We're still working on this. It's obviously you have to be very careful that you don't write something that accidentally scales your service to nothing or uses all of your cluster resources because of some downstream dependency or momentary blip. There's a lot of damping in there. But this is between these two, between doing the work of scaling and automating the decision to scale, suddenly your operations team has a lot less stuff to do, which is pretty sweet. I spent 2 years at Uber as the ultimate on-call for every escalation policy, and I can tell you that this would have made Friday nights a lot more enjoyable for those 2 years. So this is all you deploy Marathon interaction, and it's actually pretty easy to write your own. Frameworks for Mesos. The interface is really quite straightforward, and so someday we might just take udeploy and promote it into a full Mesos framework. For now, Marathon has a lot of this stuff already built in, so we're just using that. Now there are a jillion other Mesos frameworks out there. People are really like it's really fun to see in the infrastructure world. There's a ton of focus that's going on to this cluster management space. So there's Mesos. Google has Kubernetes that's just sort of gone out. What am I missing here? Docker themselves have just released a Swarm, which is a similar type of orchestration engine. So people are really starting to catch on that like we're as a world, as an infrastructure world, we're moving away from small systems. We're moving towards needing large clusters of compute capacity, and a lot of people are putting effort into this. And so people have written a ton of Mesos frameworks, which is pretty cool. There's these task schedulers. There's Marathon. Twitter has their own, which is a fantastic. I mean, it's pretty much feature comparable with Marathon, called Aurora. You can run Hadoop on it, Spark, Storm, Kronos. Kronos is an Airbnb project for running cron type jobs on your Mesos cluster. People are doing file systems or data stores. So you can get frameworks for HDFS. Twitter has just released one called Mesos for running MySQL on Mesos. Imagine not setting up individual MySQL servers and just having this giant Mesos cluster that runs all your various workloads, and you're like, click, I want like MySQL, and it automatically deploys in replication topologies to appropriate machines. It's pretty amazing with like the resource isolation that you would need there. Hypertable, Cassandra. You can get Elasticsearch framework. There's a Jenkins framework, so you can just spin up your Jenkins slaves really easily on a Mesos cluster. And then there's these, Cray has this Chapel language. There's these parallel programming languages that have been essentially ported to work under the Mesos framework to use that to apportion resources out. The Mesosphere guys are doing a pretty amazing job with this. They're in San Francisco, venture-backed group of some, I think, Twitter employees and people from all over, and they're really focused on advancing the state of the art with Mesos, which is pretty cool to see. So the long journey to get here. We start from this simple shell pipeline, advance to these high-level language DSLs that automate a lot of the nitty-gritty nuts and bolts of these systems for us. Then once you get to a certain scale, you really need to invert the control flow. So instead of a push model, you have sort of a pull model. Then you sort of want to, once you get to even greater scale, you kind of want to start abstracting away even the concept of individual servers to some degree as much as you can, building on the blocks you already have, so that you don't have to think about a million things going wrong at once. You just think about the health of the whole. And then you also have to work on these higher availability distribution models as you get there, since one server will not be able to feed out code to your thousands of servers in your infrastructure, which of course is a good problem to have. So go forth and deploy like an evil genius. And I think we're a couple minutes early. Happy to take any questions if there are any on this titillating topic. Yes, sir?
So for your autoscaler, Mesos, are you using For your auto-scaling framework for Mesos, are you using like some sort of complex event processing system for that, like Jules Fusion, or?
Great question. I have an intern who started on a week ago today, who's like a junior, and we're going very simple to start with. We've set up monitoring essentially so that on each worker node, on each slave node, we are reporting in to our central stats server utilization metrics for all the instances running on that particular worker node. And then there's an aggregate in that stats server, on a graphite server that says, 95th percentile CPU utilization for service A is 70%. And we are, right now, it's literally pull that out or maybe look at the 5-minute, 10-minute trailing average, and have a target in mind. Oh, I want this should always be at 60% utilization. And then if it's off from that, calculate based on the number of CPUs that each instance gets and the number of instances that are currently deployed. I either need to scale up this much or scale down this much. So first revision, it just spits out a recommendation. Second revision, we'll have it actually make the change itself. And then we'll sort of make it more sophisticated, let it react more quickly. At first you want to be very, very careful with this because I have this, this kid sitting next to me who's controlling Uber's infrastructure, which it turns out the management is sort of sensitive about. So yeah, that's sort of our model. I think it'll be a little while before we get into sort of a more sophisticated controller mechanism for doing that and make the math more interesting. But that'll be there for sure at some point.